This video is to introduce Chapter 7, which focuses on inference for numerical data. We're looking at inference for numerical data. 7.1 is going to focus on one sample means using a new distribution called the t-distribution. 7.2 is going to focus on making inferences when the data that we have are paired data. 7.3 focuses on inference about a difference in two means. 7.4 does power calculations for a difference in means. And finally, section 7.5 focuses on how we can compare means between many groups using something called analysis of variance, or ANOVA for short. So as I say, in section 7.1, we're going to be making inferences about a single mean, so from one sample, using a new type of distribution called the t-distribution, which you'll learn about in the videos. You'd use this type of method when you're working with one numerical variable. The parameter of interest in this situation will be the population mean, which we give the notation mu. The point estimate will be the sample mean, x bar. And in order to use the t-distribution, we are going to need to have the cases be independent of each other. So we check that again by making sure we've got a random sample and that the sample size is less than 10% of the population. We also need to either have the sample size be at least 30, or if the sample size is less than 30, we need to see that the data come in the sample are not strongly skewed and there aren't sort of crazy outliers. So those are the conditions that we'll need to check in order to use this method. The formulas that we'll use when we're making inferences for a single mean: to make a C% confidence interval for the population mean mu, we will use a formula that has the same basic form where we've got our point estimate, the sample mean, plus or minus a margin of error. The margin of error is going to be T star. T star is similar to the Z star that we used when we were making confidence intervals for proportion. This comes from a t-distribution, which you'll learn about in the videos. It depends on the confidence level and the sample size. S is the sample standard deviation. We saw that notation in chapter 2. And of course, N is the sample size. When we want to do a hypothesis test, testing a null hypothesis that the population mean is equal to some null value, H, which we give the notation mu sub 0, we'll calculate now a t-test statistic, which has our sample mean minus the hypothesized value from the null, divided by the standard error, s over the square root of n. When we work with a t-distribution, we will need to know something called the degrees of freedom, which you'll learn more about in the videos for the chapter. Section 7.2 works with paired data. So paired data occurs when you're working with two sets of observations for which each observation in one set has a special relationship to one of the observations in the other set. So for instance, if I am interested in knowing how much a new car depreciates in the first 1,000 miles that you drive it, I might have data that I collected about 100 different cars, and I would collect the value of the car before it's sold and the value of the car after 1,000 miles. And I'd have two sets of observations, the ones that were when the cars were new, and a set that are the value after 1,000 miles. But since I have two measurements on each car, those two measurements are naturally related to each other. And so when we have paired data like this, we're going to focus on the difference between the two observations within a pair. So the parameter of interest becomes the mean of the differences among all pairs in the population. The point estimate is the mean of the differences that you calculate from your sample. In order to use a t-distribution to work with paired data, we are going to need the pairs to be independent of each other, and we'll need to have at least 30 pairs, or if we have less than 30 pairs, we need to see that the sample data, the distribution of the differences that we calculated isn't strongly skewed. The equations that we use with paired data look just like the equations for single mean, except that we are replacing the mean mu with the mean of the differences. So, for instance, we have our sample mean of the differences, plus or minus a t-star value that depends on the level of confidence we want in the sample size, times the standard error of the which is the standard deviation of the differences divided by the square root of the number of differences. In hypothesis testing, if our null hypothesis is that the mean difference is equal to 0, then our test statistic, t, is the mean difference in the sample, x bar sub diff, minus the hypothesized value of 0, divided by the standard deviation of the differences over the square root of the number of differences calculated. And the degrees of freedom are the n minus 1, just as they would be for a single mean. Section 7.3 focuses on inferences for a difference in two means, testing to see if the means are different or making a confidence interval for how big the difference is between the means in two groups. We use a difference in means when we're working on comparing two groups using a numerical response variable. So we've got a categorical variable that we're using to form the two groups, and then a numerical variable that we're using to compare them. In this situation, the parameter of interest is the difference in the two population means, mu1 minus mu2. And the point estimate for the difference in the population means is the difference in the sample means, x bar sub 1 minus x bar sub 2. In order to use a t-distribution to make inferences, we need the observations within each group to be independent of each other. We need the groups themselves to be independent of each other. If we didn't have independent groups of observations, remember we might be in that paired data kind of situation. And we also need to have in each group a sample size of at least 30, or if the sample size in one of the groups or both of the groups is less than 30, we need to know that in that group the sample isn't strongly skewed. The equations that we use to make a C% confidence interval for the difference in the two population means. We use the difference in the sample means as our point estimate, and then we add and subtract a margin of error, which we find by taking a t-star value times the standard error, which we calculate using the square root of s1 squared over n1 plus s2 squared over n2. When we're conducting a hypothesis test to test for a difference in means, the null hypothesis would be that the means are equal to each other, so mu1 equals mu2. And our test statistic will be a t-test statistic. It'll be the difference in the two sample means in the numerator divided by the standard error, which we calculate by taking the square root of s1 squared over n1 plus s2 squared over n2. The degrees of freedom that we will use if we're doing this by hand, we'll use the smaller of the two sample sizes and then subtract 1. So whichever is smaller, N1 or N2, we take that and subtract 1. This is not going to be an exact calculation of the degrees of freedom. The formula to calculate degrees of freedom by hand is very complicated, so our book doesn't use it. However, if you were using technology like R or a calculator that does these kinds of calculations for you automatically, then you will get a slightly different p-value than you will from doing it by hand, because they will calculate the degrees of freedom exactly using the complicated formula. Section 7.4 focuses on power calculations for difference in means, and I will start off by saying that this is a very challenging topic. Doing the calculations requires a really methodical approach, and it can be very confusing. So don't worry too much if you find this topic challenging. This topic is extremely challenging. Don't get too bogged down in it. The most important things from my point of view are for you to develop some understanding of how power is related to things like the sample size, the standard deviations in the populations that you're trying to compare, the significance level you choose for the test, and how large a difference you're trying to detect between the groups. So all of these things are going to be related to the power. And having a sense of whether sort of how changing these things would increase or decrease the power of your test is, I think, worthwhile to try to sort out. The main importance of talking about this topic is to impress upon you that if you are doing research, it's really important to do a sample size calculation at the design phase, right? Because if you do a study and your sample size is too small, then you might lack the ability to show strong evidence in support of your research hypothesis. On the other hand, if you do an excessively large study, larger than you really needed to do, you're spending more time and more money doing research than was actually needed to provide a good answer to your research questions. So it's a balance between having enough power and not using too many resources, and doing a sample size calculation is very important. And then the last topic in this section is looking at how to compare many means with ANOVA. And so this is when we'd use this is when we're interested in comparing more than two groups using a numerical response variable. When we use ANOVA, or analysis of variance, we calculate an F statistic and use an F distribution to find our p-value. You'll learn a lot more about that in the videos for the lesson. The assumptions that we need to satisfy, we need the observations within each group to be independent of each other. We need the groups to be independent of each other. We need the distribution of the data in each group to be approximately normal. That can be relaxed a bit if the sample size is very large, but it is a condition for using ANOVA. We also need approximately equal variance in all of the groups. So again, this is something that if the sample sizes are relatively similar in all of the groups, then this can be relaxed a little bit. If the sample sizes are very different between the groups, then we end up, this becomes a more important condition for the analysis of variance. When we are comparing many means with ANOVA, the null hypothesis for our test is that the means are equal in all of the groups that we're comparing. And the alternative is that not all of the means are the same. So at least one of the means differs from the others. The test statistic that we're going to see, this F test statistic, is calculated by taking the mean squares between the groups and dividing it by the mean squares within the groups. Essentially what this is going to be doing is if there's sort of a large amount of difference between the groups, compared to the amount of variability within the groups, it's going to give us a large statistics, and it will tend to give us a stronger evidence in favor of the alternative hypothesis. So you'll see a test statistic that looks like this. Calculating the mean squares, there's a couple of steps that you go through along the way. You calculate what's called the sum of squares, both between groups and the sum of squares within the groups. And you calculate degrees of freedom for between the groups and for within the groups. Then the mean square is the sum of squares divided by the degrees of freedom. So you will need to learn about the relationship between these things. However, calculating the sum of squares is extremely tedious to do by hand, so you won't be doing any of those calculations by hand. Those will either be given to you or done in the lab. You'll be doing them with R. So again, the most important things to take away from this are similar to last week: to be able to recognize when you would use each of these methods, to be able to correctly interpret the results from these methods. The least important thing to take away is the ability to crunch the numbers. So once again, if you're having trouble getting the numbers to come out right, don't worry too much. Let me know, and I'm happy to help you work through the numbers. This week coming up, test 2, which is available now, is due to be finished on Friday. Remember that you will have a 2-hour time window in which to complete that after you start it, but you can start it anytime between now and Friday. There is no discussion board assignment this week because I just felt like with the test going on, it's way too much work for you to also have to do a discussion board activity this week, so no discussion board. The week 5 R Lab is due on Friday. The chapter 7 homework is due on Sunday in My Open Math, and that'll take us through the week. If you are a graduate student and you need to do the additional R Lab at the end of the semester, that is being posted today, so you'll be able to start that whenever you're ready. And otherwise, just remember, I'm here to help. I have my office hours on Tuesday and Thursday mornings from 9 to 10. And if you'd like to meet some other time, I'm happy to meet at other times. Just send me a message and let me know what times work for you. And of course, I'm always happy to answer questions on the help discussion board also. Have a good day.